This part of the lecture will cover about some matrices that you see a lot in applications. These are important list. In the previous video, we intensively covered the property, the definition, and the usage of symmetric and positive definite matrices. Uh, the matrices that we list here has a certain structure, has a certain pattern. In this particular video, we will touch upon unitary, idempotent, nilpotent, and doubly stochastic. We will only give the short definition and the final results that can be quickly proved. For all the details and maybe some more intensive applications will not be included in this video. You can further read the book by Horn, Matrix Analysis. Okay, so let's start with the first one, unitary matrix. Now we extend the domain to talk about a complex matrices. So when you talk about complex, there's going to be some operator that need to be introduced. So this is called a Hermitian operator, Hermitian conjugate. So what it does to the matrix is to take the transpose and then conjugate. For example, if U is 5i 1 minus 2i, where I is the root of negative 1, 4 plus I, this is 1 plus 6i. So U star in this slide is simply take the transpose and then take the complex conjugate. So that's going to be minus 5i, 1 plus 2i, 4 minus I, and 1 minus 6i. That's it. Okay. Um, that's the U star. Let's talk about the definition. The unitary matrix U is a matrix where you find U star that left and right multiply with U and give you identity matrix. Okay, we have some example here, the matrix U that I'm going to show later that is called discrete Fourier transform matrix. I hope you understand this notation, e to the I theta e to the I theta, that is by Euler identity. Okay, you can find its value from this expression. Okay, so when this example, when you please verify if you put the star and then multiply with U, that gives the identity matrix. Okay. By this notation, we already found the something that multiply U on the left and multiply U on the right and gives you the identity matrix. That quickly shows that the matrix U is invertible and the inverse is simply the star operator, the complex conjugate transpose. Very simple. Another quick property that we see is that the column of U must be mutually orthogonal. This can be quickly seen from if I use the notation that my U is partitioned into columns as U1, U2, dot dot dot, UN. So this is my U. So U star is going to be U1 star, U2 star, dot dot dot, UN star. Okay, so when you multiply it out, it's going to be U1 star U1, U1 star U2, dot dot dot, U1 star UN. And for the second row, you're going to have U1 star U1, U2 star U2. Basically, you're going to have UK star UK in the diagonal. And then you can see that if the results of multiplication give you the identity matrix, all the upper and lower triangular part must be 0. That quickly shows that UI transpose UJ must be 0. So that's what it means. Columns are mutually orthogonal. So if you transform any matrix, so if you transform any vector with U star x with UX, Of course, we talk about X in a complex field, in a complex vector. So Ux is also a complex vector. So the norm of Ux, okay, that's gonna be the notation of Ux star Ux, because when X is a complex, okay, to compute the norm square is gonna be take the complex conjugate transpose of X, or what we see that X star X, right? So when you compute the norm, all right, you can see that that's gonna be X star U times X, but U star U is identity matrix. All right. So the image under the transformation U will give you the same norm as the norm of the original vector. So the two norm is preserved under a unitary transformation. Okay, so this is the property of U. Let's see an example in detail. In the previous slide, I give you this matrix and show that this is unitary. That happens to be a special case of discrete Fourier transform, or DFT. Suppose you have a signal, discrete time signal xn. This is what we call discrete Fourier transform. We take the sum of xn, and this is exponential term. Okay. So this factor is quite geometric sequence in n. Sorry, in k. Oh, sorry, in n. Um, so for a nice notation, let me just use the variable z. Okay, so you can see that in a discrete Fourier transform, you're gonna progress this term for for n equals 0, and when n increase the integers. So for x0 k equals 0, so it's gonna be just sum of the discrete time sequence. For x1, when k equals 1, you're gonna progress. You're gonna take this sum with the factor of z1, z to the power of 2, and z to the power of n minus 1. Multiply this, and so on. Okay. So so it seems that DFT can be written as just F5 transformation, and that transformation matrix is called DFT matrix. We can show that this matrix is unitary. Okay, so when it is unitary, that allows you to write to write uh, to write the discrete time signal. This is in time domain, the small x. All right, the capital X is in the frequency domain. So if you transform from time domain to this to frequency domain, you use D. But on the other hand, if you want to solve for x, small x, you take the inverse, right? Take the inverse. So it's going to be the inverse capital X. But we already know that the inverse of unitary matrix is simply the Hermitian conjugate, right? So that means take the inverse discrete time Fourier transform. It's also simple. Just take the star operator. Okay. In this slide, I confirm, verify the unitary property of the DFT matrix. Okay. For the special one, you see that each row of, or you can take a look at each column. So each column of unitary matrix, of DFT matrix, is kind of a geometric series, Z1, Z2, go all the way, right? So this is also geometry series, entries in each column. So if I construct phi k, okay, phi k seems to be any column in the DFT. So it takes the form of uh of suppose this is z, and this is going to be z square and z to the big N minus 1. So what we can show quickly is that we can use, we can verify that columns in the DFT matrix are orthogonal by showing that the inner product between phi L and phi K, which is going to be this operator, phi K bar transpose phi L, okay, by star, what we mean by here. And we're going to show that it is 0 or 1. We're going to show that is 0 when K is not equal to L. It's going to be 1 when K is equal to L, or when K is a multiple of L. Okay. So is it obvious that when okay, when you take inner product of this guy, it's gonna be K star phi L, right? But phi K star is to take the transpose and complex conjugate. So so it's gonna be it's going to be 1 e to the I 2k pi over n e to the I 2 pi k 2 over n. So you just, for phi k star, you just flip the minus sign to the positive sign because that's the complex conjugate, right? So that's why you're going to have the positive power in k, in index k. And for phi l, you're going to have negative power, okay? So is it obvious that when k equals L, this sum is basically the sum of 1, right? The sum of 1 from 0 to n minus 1. So overall, this guy gives you 1. When k is not equal to L, all right, we're gonna apply the formula of geometric series, which is this one. Okay, please recall that you have the formula when geometric series. Okay, so when I apply that formula, the sum is this. And you can see that when k is not equal to L, what happened to this term? So when k is not equal to L, that term is going to be e to the I2 pi, and then it's going to be just a positive integer, right? So that term gives you 1, and 1 minus 1 is 0. So that summation is 0 when k is not equal to L. Okay. So this is to show that the FT matrix is unitary. Let me move to another one that is very closely related to unitary, that is called orthogonal matrix. How long has it been? Okay, 13 minutes. If you scope down to the set of real matrix, when everything is real, so it seems like U star that is supposed to be the complex conjugate transpose. When U is real, U star is simply the U transpose. So orthogonal matrix has a definition that is exactly the same as unitary matrix, but it's just that orthogonal matrix is used for the real matrix. Okay, so U is called orthogonal when U transpose equals to U transpose U equals I. Okay, so it's just a special case of unitary for real matrices. And we also have the same property, U inverse equals U transpose. Columns of U are mutually orthogonal. And the two norm is preserved under the orthogonal transformation. What you see is that if you have a vector x, here, okay, so this is going to be, sorry, it doesn't look like a circle when I draw. Okay, this is a vector x, any x that lies inside this norm is a vector that has the same norm as x. So when we have these two norm property, okay, uh, it basically says that when you map x with any orthogonal matrix, the matrix ux is gonna lie inside the norm ball, the same norm ball as x. Okay, here's some example of orthogonal matrix. You can quickly see that uh, the two columns are orthogonal. All right, when you perform the dot product or inner product between any pair of columns in orthogonal matrix, it's gonna be 0. Okay. Projection matrix, okay, or idempotent. A square matrix P is said to be a projection matrix if P square equals P. If P square, like, if it seems like your X is here, okay, your PX could be another vector in another direction with another norm. But if you apply p square on px, if you apply p on px again, that's going to be p square x, right? That's going to be the same vector as px. Mhm. What is it's called projection or idempotent. Um, let's see. Because of because of this property. Suppose you have suppose you have a subspace S, okay? Subspace S. It has a meaning in application that when P is a linear transformation to a subspace S, okay, columns of P are the projections or are the projections of standard basis vectors, and S is going to be the range of P. Okay, if we apply P twice, it gives the same vector. So let's see some example. Okay, maybe let's see this one. Okay, 3 minus 6, 1 minus 2. Okay, and this is P square, right? What is the matrix at the end? So that's going to be 3 and what is it? Minus, if you multiply this with this, so it's going to be minus 18 plus 12. That gives you minus 6. So if you verify that this matrix P square is equal to P, or let's see, let's examine another one. Let's Okay. What about this matrix? This matrix in the regression actually has a meaning of orthogonal projection that we're gonna talk shortly. Um, but can you square this? Okay, this is gonna be I minus X transpose inward X transpose, and I multiply with this again. Not the inverse, it's the transpose. Okay, so you're gonna get I, you're gonna multiply this with this, it gives you I, and then you're gonna multiply this with I, and then you're gonna multiply this with I, but you see that that's gonna be twice, right? Twice x inverse x transpose, and the last term would be this and this with the sign plus. Let's explore, and then x transpose x inward x transpose. You're gonna see that there's some cancellation, all right? There's some cancellation, and this is gonna be exactly like this term. So at the end, you have I minus x X transpose X inverse X transpose. So this is just simply to show by the definition that P square P equals I. Okay. Um, okay. When P square equals P, it turns out that eigenvalues of idempotent matrix are all equal 0 or 1. It's either 0 or 1. Why? Because you have so when you want to prove something about the eigenvalue, you think of eigenvalue problem. So suppose px equal lambda x, that is the eigenvalue problem, right? So if I try to multiply the whole equation by px, I have p square x, right? But this is px is lambda x, that is lambda square x, right? But my p square, is also px because my p square equals p. Okay, so and I also substitute px equals lambda x. So I get to the characteristic equation that lambda square minus lambda x equals 0. X is never 0 because it's eigenvector. So that's why lambda square minus lambda is always 0. So that's proof the property of the eigenvalue. Uh, this property is not hard to show. Can you verify that if P is idempotent, so is I minus P? Okay. You also see that identity matrix is also an example of idempotent matrix because I square equals I. In that case, the eigenvalue of I are all 1, right? So the last property is that for any idempotent that is not identity, because 0 is going to be one of the eigenvalues, so those matrices, those idempotent matrices will be always singular matrix. Okay. So maybe I will illustrate real quick with the MATLAB that I'm going to construct a matrix T in this way, okay, and show you or some of this, some of that, and show that eigenvalues is either 0 or 1. Okay. So let's start with P equals 3 minus 6 and what? And 1 negative 2, right? 1 negative 2. Okay, so I show the eigenvalue is either 0 or 1. Now I'm gonna generate something that looks like this term. So my x, this matrix appears a lot in regression, all right? So that happened to be a matrix that that use x as a tall matrix. Okay, so I'm gonna generate x as a tall matrix, and it's also full rank. So my p is gonna be identity of. So what is this identity matrix? This identity matrix must have the same row as x, right? The same row as x. So in this example, so it's going to be 4 x times inverse of x transpose x times x transpose. This is my p. Now I'm going to show you that the eigenvalues of p is either 0 or 1. Okay. Hmm. Hmm. Okay, so this is idempotent, p square equals p. So the next one is also closely related to the previous one. A matrix P is called orthogonal projection. That for the projection matrix is p square equals p, but for orthogonal projection matrix, Not only that p square equals p, but it also equals to the p transpose. Okay. So in the previous example, this has the property of p square equals p. All right. So which one that is particular p transpose? This one, right? This one is also symmetric, but not this one and this one. So it means that all the matrices in the circles, not only that is projection, but it also orthogonal projection matrix. Okay, so orthogonal projection matrix will also have property of the projection. All right. Um, let's see. What about its further property that we can derive? Um, believe it or not, if you have a vector x here, okay, you have a vector x here. Usually for any other mapping, for example, AX, right? You know that typically AX could go to any different direction from X, and the length of the length or the norm of the image under the transformation A can be larger, can be smaller to the original one. We cannot tell. But when P is orthogonal projection, we can prove that the the normal px is always shrinking, is always smaller than the original one. So what we have is going to be something like your, so suppose so I'm going to draw the circle again, circle. Okay, so in the circle is any one in the circle is a vector x that has the same norm as x. Okay, what I mean by this result is that px is gonna lie inside this norm ball. Okay, it can be equal, but it cannot be bigger than the norm of x. The proof is very simple. Okay, we start from the norm square px, right? The two norm, we use the two norm. And the norm of this is obviously, of course, by the definition is px transpose px, right? So it's when you expand this, it's x transpose px, but p transpose p equal p square, and p square equals p. And from here, we use the Cauchy-Schwarz inequality that says x transpose y is going to be less than norm of x tan norms of y, right? So we think of this as x, we think of this as y. So it's bounded by norm of px norms of x. So one term cancel. So that's why you get that norm of px is less than the norm of x. When you have a mapping P where the norm of the image is always less than norm the original one, we say that that transformation is bounded. Okay. Um, hmm, we already see some example of orthogonal projection in when we talk about the inner product space. So we have a formula where when you want to project, suppose this is a line in the direction of a vector u, and if you want to project y on u, right? We say we already saw in those lectures that the projection of y onto the onto the onto a line in the direction of a vector u is going to be the inner product between u and y times u divided by the norm square. Okay. But if we just normalize this norm, if we just normalize u to have a unit norm, this goes away because the norm is 1. Okay. Remember that this is just inner product. This is a scalar. So I can also move U transpose here. This is a vector, this is a scalar, so I can also move U here. So, but then it gives you a form that orthogonal projection of a vector onto a unit norm vector is U transpose Y. So it's look like you apply some matrix P on Y, okay, and that is orthogonal projection matrix. So its meaning is that, all right? Its meaning of this P is to project a vector v u y on a line explained by u. Okay. When you have a matrix that is outer product of a vector, we know that we can prove that the rank of this matrix is 1. Okay. Um, this can be exercised. I usually give this as a homework exercise that there's going to be the lambda of U transpose U is going to be there's going to be one term that is non-zero and the rest of them are all zero. So this is n minus 1. They have n minus 1 zero eigenvalue. And this one, there's only one non-zero eigenvalue. Okay. Some example of orthogonal projection matrix is this one. Okay. You can quickly check that p square equals p and is also symmetric. What's the meaning of this in the regression sense is that you have the range of Rx. You have the range of Rx. Rx means the range space of the matrix X. And if you have original vector Y, okay, so the question is, what is the vector on range of X that is closest to Y? We say, oh, we're going to do the projection, okay? This one. This is the projection of Y onto range of X. And from the analysis, all right, you can perform what we did in the orthogonal projection problem. That one, it turns out to be this matrix. Okay, so it looks as if you multiply with the matrix in the yellow term. Okay, and it also has a meaning in the regression because that orthogonal projection matrix turns out to be the same solutions as the problem of minimize y minus range of y minus x times beta square, and we minimize over beta. So this is least square problem. Give me a linear model, right, parameterized by beta that gives me the y hat. This is y hat. Give the y hat closest to y in the true norm sense. That choice of beta is going to be this one, this term. Okay. So it's very So, I mean, all the VCs from orthogonal projection problem that we solve, find, if you just write down any projection in terms of some linear mapping on Y, okay, that linear mapping is going to be orthogonal projection matrix. Okay. So let's stop here and then we're gonna continue in the next video for other matrices. Do I have some more? Do you have some more examples in MATLAB or not? Okay, we can do the same thing for P here. Suppose I have X, right? I have X that is tall. I give my P is X inverse X transpose, right? So first P times P. So I check with the norm, right? I'm just gonna show that p squared equals p, so I use the norm to calculate the distance. Very small, right? What about p and p transpose? Yes, p equal to p transpose. What else? Eigenvalues of p. See, is either 0 or 1 because it's a projection matrix. Mhm. Okay, let me also show the bounded property. Okay, so here I'm gonna generate x multiple times, and I also generate a vector x, a vector z that will be multiplied to this. So my z is gonna be 3 by 1. So I'm gonna compare p times z, the norm of pz, and the norm of z. And I'm gonna show you that it is always, oh, sorry. The length of z should be 5, okay? Because z will be multiplied with x transpose. Okay? So what I'm showing here is that p is bounded. The norm of pz is always less than the norm of z. So let me randomize again. Randomize again. Randomize again. So norm of pz is always less than the norm of z. All right. Okay.